Hi, this is Gopinath Mishra from Indian Statistical Institute. The title of my talk is Even the easiest graph coloring problem is not easy in streaming. This is a joint work with Anup Bhattacharya, Arijit, Bishnu and Anannya Upasana. In the classical graph coloring problem, we get a graph G as input. The objective is to color the vertices of the graph using minimum number of colors such that the edges of the graph are not monochromatic. By monochromatic edge, we mean the endpoints of the edge are colored with same color. For example, in this figure, the red colored edges are monochromatic edges and the black colored edges are non-monochromatic edges. All of us know that the classical graph coloring problem is NP hard. Also recall that the classical graph coloring problem is in NP. While proving NP, we have considered a coloring verification problem where the inputs are two things, the graph G itself and a coloring function H on the vertex set of the graph. The objective of us is to decide if there exists a monochromatic edge in G or not. Note that in this paper we focus on this particular coloring verification problem and a natural generalization of it in one-pass streaming model. In particular, we consider a problem called conflict estimation where the inputs are a graph G itself and a coloring function F on the vertex of the graph G, where the objective is to estimate the number of monochromatic edges in G with respect to F. Note that the conflict estimation problem is a strictly difficult problem than the coloring verification problem. First, note that conflict estimation problem can be solved in time linear in number of edges. In RAM model, obviously, we focus on conflict estimation in different variants of streaming model. Before getting into literature and our results, first observe that we are considering conflict estimation problem in any streaming model, and the coloring function F is written on a public board. In that case, we can solve the coloring conflict estimation problem very easily. So, let us discuss briefly about literature of graph coloring problem in streaming. So then we will get into what exactly we are doing. So in literature, recently there are 4 works. All of them are similar in 2 points. That the results are in edge arrival semi-streaming model. By edge arrival, we mean the vertices are known and the edge set of the graph are coming in an arbitrary order. By semi-streaming, we mean the space complexity of the algorithm is sublinear in the number of edges, but not necessarily sublinear in the number of vertices. That is first thing. Second thing is all of these 4 works focuses on finding a coloring function that satisfies a desired property. The desired properties are different in different paper, but their focus is to find a coloring function. Note that our problem considered in this paper, in particular conflict estimation, is different from those work done recently, where the focus is to find a coloring function, but in conflict estimation, a coloring function F is given along with the input graph, and our objective is to estimate the number of monochromatic edges in G. So once again, we reiterate, the focus of this paper is to study conflict estimation in one-pass streaming model. First, let us consider well-established edge arrival model. Note that when an edge arrives, UV, if we get to know about the colors of U and V, then we can check instantly whether UV is forming a monochromatic edge or not. So in edge arrival model, conflict estimation problem can be solved using logarithmic space. So we consider conflict estimation problem in different variants of vertex arrival model. So before getting into our results, first let us briefly describe what are different variants of vertex arrival model considered in the literature as well as in this paper. In basic vertex arrival model, the vertices of the graph G are exposed in an arbitrary order, say V1 to Vn. When a particular vertex V is exposed, we get to know two things. First, the color of the vertex V. Second, all the neighbors of V that are already exposed before V. This is the description of basic vertex arrival model. There is another vertex arrival model known as vertex arrival with degree oracle, in short VADEG. This is same as VA model with an extra power where we can have the knowledge of the degree of the exposed vertex V by querying to a degree oracle. This is the description of vertex arrival with degree oracle. In short, vertex arrival degree oracle is model is same as vertex arrival, where we will also get to know about the degree sequence of the vertex set. There is another vertex arrival model known as VA RAND model. So random order vertex arrival model, where the order of exposure of vertices follow is a random permutation of the vertices. That let the vertices of the graph are exposed in the order V1 to Vn. Here V1 to Vn is not an arbitrary order, rather this is a random permutation of 1 to n. And the coloring exposure and the edge exposure in VA random model is same as basic VA model. Now let us briefly discuss the set of our results. So we study conflict estimation problem, all three vertex arrival model that we have introduced now. Now let us look at the bounds. In vertex arrival model, basic vertex arrival model, upper bound, lower bound matches. In vertex arrival degree oracle model, both upper bound and lower bound matches. However, in vertex arrival random model, upper bound, lower bound does not match. There is a gap. We will discuss about this gap about around the end of the topic. Another, in the different perspective, note that the space complexity for conflict estimation in random model vertex arrival model is less than that of corresponding value in vertex arrival and vertex arrival degree oracle model. So here we would like to note that the VA RAND model really outperforms VA and VA DEG model. So another thing in this slide, there is a parameter. Note that there is a parameter T. What is T? T is a promised lower bound on the number of monochromatic edges. Note that this kind of assumption on the lower bound is usual in streaming. This has been considered in literature many times. So we focus in this talk about discussing these two things, that is upper and lower bound for conflict estimation in VA RAND model, which is our main contribution in this work. So first let us discuss the upper bound for conflict estimation in random order vertex arrival model. We were getting into the idea. First observe that the number of monochromatic edges is equal to half of the sum of the monochromatic degrees of the vertices. So here you would like to note that our problem is about basically estimating a summation. So before getting into the details, let us have a look at our idea in a high level. So the idea is to take a random subset of the vertex set of desired size, in particular n by root t, where n is number of vertices, and examine the neighborhood, monochromatic neighborhood of the vertices with respect to this randomly selected set R. So here n subscript MB denotes the set of monochromatic neighbors of B. We would like to understand the monochromatic neighbors of B inside R. In particular, this quantity kappa B, which denotes the number of monochromatic neighbors of B in R, plays a very crucial role in design and analysis of our algorithm for concept estimation in random order vertex arrival model. We call this kappa B as projected monochromatic degree of B. So here in the high level idea, we told about two things. That we take a random subset R of random subset of vertex set R, random subset R of vertex set of desired size. That is first thing. Second thing, about this kappa B, projected monochromatic degree of vertex B. These two things play important role in our algorithm and analysis. So let us first discuss how our algorithm can take a random set R in VARAND string and determine the value of kappa B if required. So first let us discuss how our algorithm finds the random set R. Note that we are discussing random order vertex arrival model. So first mod B by root T vertices in the first mod B by root T vertices in the string can be considered as random set R. So our algorithm starts by storing the vertices and colors of all vertices in R. That is first thing. So this is the way we store R. So R is basically first set of desired vertices. Now we will discuss how we will determine the value of kappa B. Recall that kappa B is the number of monochromatic neighbors of B in R. So note that R is the first set of n by root T vertices, right? We want to estimate kappa B. First note that if V is a vertex inside R, then nothing to discuss, because we have told that we are storing all the vertices as well as their colors in R. So we are storing all the vertices in R along with their colors. So if V belongs to R, then nothing to discuss. Now consider the case when V is outside R. So when V is exposed, we will get to know about the color of V. And as we are considering vertex arrival random order model, we will get to know about the information about its neighborhood inside this set R. And also note that we have stored the colors of all the vertices of R. So easily we can determine the number of monochromatic neighbors of B inside R, that is the quantity kappa B for any vertex in this string. Okay. So now let us have an observation before getting into details of our analysis. So consider a large vertex. Large vertex, by large vertex I mean vertex having large monochromatic degree. Recall that kappa B is the projected monochromatic degree of B into R, that is number of monochromatic neighbors of B inside R. So by the fact that the monochromatic degree of B is large, we can say that monochromatic degree of B can be estimated from the projected monochromatic degree. The calculation wise this is fine. By using Chernow bound we can do that. If monochromatic degree is large, we can estimate the monochromatic degree of the vertices, vertex B, from the value of projected monochromatic degree kappa B. But here the challenge is, how can we know that whether the vortex B is having large monochromatic degree in the entire graph? Obviously, this is a challenge because we don't know the value of monochromatic degree of the vertices. To cope up with this, we classify a vortex to be either high or low. Here high means having high projected monochromatic degree, or low projected monochromatic degree based on its projected monochromatic degree, that is kappa B. So based on kappa B, if kappa B is large, we say that the vortex to be high, and if kappa B is less, and we say that vortex B to be low. So the classification can be done in streaming because classification is based on the value of kappa B, because that kappa B denotes the number of monochromatic neighbors of B inside R, and we have discussed that we can determine the value of kappa B in this string. So classifying a vortex, whether it is a high or low with respect to kappa B, is not a problem. So keeping that in mind, let us consider two sets, H and L, where H is the set of high vertices and this L is the set of low vertices. Also break the number of monochromatic edges into two parts, roughly into two parts. Why roughly? Because there is a half factor in the calculation. We will see. MH is the sum of the monochromatic degrees of the high vertices. ML is the sum of monochromatic degree of the low vertices. If we define MH and ML like this, then we can say that the number of monochromatic edges is half of sum of MH and ML. So we will be done by discussing how to approximate MH and ML separately. Let us first discuss how can we approximate MH. So MH is the sum of monochromatic degrees of high vertices. So we have discussed that kappa B can be determined for any vertex in the string. Once again, I recall that kappa B is the number of monochromatic neighbors of B inside R. Also, based on kappa B, we can decide whether the vertex is a high vertex or a low vertex. And if a vertex happens to be a high vertex, we can estimate the monochromatic degree of B from the value of kappa B. This can be proved by using standard Chernoff bound. So MH can be estimated in our streaming because we have discussed how to estimate D and B for B belongs to H. So now we are left with the discussion of how to estimate ML, that denotes the sum of monochromatic edges of the low vertices. First recall that kappa B was enough to estimate D and B when B belongs to H. But that technique won't work when B is a low vertex, because we won't be able to apply Chernoff bound, or rather we can apply Chernoff bound, but Chernoff bound won't give the desired result. To cope with that, we consider the partition of low vertices L into buckets such that in a particular bucket the vertices will have similar projected monochromatic degrees. So as in a particular bucket the monochromatic degrees of the vertices are similar, we will be done if we can estimate the sizes of the large buckets. Right? So what about the small buckets? So by name small bucket means there are few vertices. Also recall that we are bucketing only low vertices. So bucket sizes are small, we are bucketing only low vertices, so the contribution of the small buckets can be ignored. So we will be done by discussing how we can maintain the sizes of the large buckets. So consider a bucket B, that is a large bucket. Observe that the cardinality of B can be estimated from the cardinality of B intersection R. That is number of vertices of this particular vertex, particular bucket in R. So now the problem boils down to how can we estimate B intersection R. So recall that R is the first set of V by root T vertices. So we can determine B intersection R cardinality if we can determine the buckets for every vertex in R. Also, how we are bucketing? We are bucketing the vertices based on exact monochromatic degrees. Okay. First, observe that the exact value of monochromatic degree of a vertex V that is present in R can be found. How? Consider the vertex V in R. We can determine the monochromatic neighbors of V inside R easily because we are storing all the vertices of R along with their colors. Now let us consider the case how can we detect a monochromatic neighbor of V outside the set R. In this figure, consider the vertex W1. Note that when W1 is exposed, we get to know about the color of W1. Also, we get to know about the edge VW1. Note that we have already stored the color of vertex V. So we will have the information about this monochromatic edge VW1. Similarly, when W2 will be exposed, we will get to know about the monochromatic edge VW2. In this way, by the end of the stream, we get to know about the monochromatic degree, the exact monochromatic degree of the vertex V. So, for any vertex in R, we can determine its exact monochromatic degree. So, as we can determine the monochromatic degree of a vertex, we can decide the bucket for the vertex. So, what can we do? We can decide buckets for all the vertices in R. Hence, we can determine the cardinality of B intersection R. So with this, we are done with discussion of our upper bound for conflict estimation in random order vertex arrival model. Now we will go to our lower bound proof for conflict estimation in random order vertex arrival model. So we prove the lower bound for conflict estimation. In fact, lower bound for an easier problem where the objective is to decide whether the graph has no monochromatic edges or there are omega t many monochromatic edges. And we saw that the lower bound is omega mod v by t square. We prove this lower bound by a reduction from a problem in communication complexity. It is multi-party set designedness denoted by designedness TNP. We discuss about this designedness problem shortly in few slides and what are this parameter TNP. But before that, let us discuss about the hard graph instance that is going to be used in our reduction. The hard graph instance has n vertices partitioned into n by root t parts. Each partition has root t vertices, and each partition forms a clique. So there are n by root t cliques, each of size root t. So in the hard instance, the graph is fixed. The graph is not getting changed, but the coloring on the vertices is such that it satisfies one of the following: that either the input graph, which is fixed, has no monochromatic edges, or it has omega t many monochromatic edges. Moreover, if the graph has roughly T many monochromatic edges, and all the monochromatic edges belongs to one clip. That means two cases. Either no edge is monochromatic, or there are theta T many monochromatic edges that are concentrated in one clip. This is our description of the hard instance. So now, before getting into the reduction, let us have a discussion about the communication complexity problem that we are using. So the problem is denoted as designedness TNP. We will discuss what is this parameter TNP shortly. Consider a matrix M of dimension T cross N, binary matrix of dimension T cross N, and let there are P pairs. Let there are P pairs, and P is at least omega T square. Omega T square. Each entry of the matrix is a binary entry, that is okay, but it is given to one of the players uniformly at random. The objective of the player is to determine if there exists a column in matrix M that is all one. Chakravarti showed that this disjointness problem, multi-party set disjointness problem, admits a lower bound of omega n by t, where t and n are this t cross n, that is denoting the dimension of the matrix, and number of pairs is omega t square. Here we would like to point that the lower bound holds even if with two promises. That first promise is there is at most one column with all one, and all other columns are having Hamming weight 0 or 1. So there can be two cases. Either all the columns are having Hamming weight 0 or 1, or there can be a second case where there is exactly one column having all 1 and all other columns are having Hamming weight 0 or 1. This is the first promise. The second promise is the lower bound holds even if the players know the random partition. What is this random partition? We have told that the entries of the matrix are partitioned among players randomly. The random partition is known to all the players. The lower bound of omega n by t holds even if these two promises are there. In particular, in our context, we use disjointness with this parameter. Small t is equal to capital T root over, n is equal to n by root t in place of n, and number of pairs is theta t. We use in this setting. And as the disjointness problem admits, disjointness TNP admits a lower bound of omega n by t, the problem we are considering for reduction admits a lower bound of omega n by capital T. Okay. This is the description of the multi-party set disjointness problem we are considering for reduction. We will get into the reduction, but before that, the reduction will imply a omega n by t square lower bound for one pass streaming algorithm, one pass in general constant pass streaming algorithm for conflict estimation problem. Note that disjointness admits a lower bound of omega n by t, but this conflict estimation in constant pass stream admits a lower bound of omega n by t square. The reduction in factor t is due to there are theta t pairs in the communication complexity problem. Before getting the reduction, we would like to stress another point that there is a requirement of V and random order model, that the vertices of the graph will be exposed in a random order. This requirement is satisfied because of two things. First, that we are saying that the entries of the matrix are distributed among players uniformly at random, and the players know the random partition of the matrix. Due to these two things, the requirement of V random order matrix arrival is satisfied in the reduction. So now it remains to describe the reduction. The left figure shows the matrix of the disjointness problem, and the right figure shows our hard instance G. So there are n entries in the matrix, there are n vertex in the graph. There are n by root t many columns in the matrix, there are n by root t many clicks in the graph. So we consider a one-to-one mapping between n vertices of the graph and n vertices of the graph and n vertices of the n entries of the matrix. Moreover, the one-to-one mapping is between entries of the matrix and the vertices of the graph is such that there is also a one-to-one mapping between columns of the matrix and clicks of the graph, such that all the entries of a particular column are mapped to the vertices of a particular click. Now let us discuss the strategy of the players. So the strategy of the player is to use the streaming algorithm for conflict estimation to solve disjointness problem. Here the strategy of the player is such that they want to color the vertex of the graph. Why we are not bothering about the insertion of edges? Because our hard instance, the graph hard instance is fixed. We are only playing around the colors assigned to the vertices. So the players have a strategy to assign colors to the vertices of the hard instance in such a way that if there is a column of all one, then the corresponding then the vertices of the corresponding click have same colors. That means all the edges of that particular click are monochromatic. So we have omega t many monochromatic edges. And if there are no all one columns, then no click, no edge will be monochromatic. No edge will be monochromatic. So how we will ensure that? Consider a column where there are only 1 remaining are 0, and consider its corresponding click. So when we, for two zeros in the same column, we give two different color to the corresponding vertex, so that the zero won't be responsible. So zero won't be responsible for monochromatic edges. For example, if we color with color 1, we color with color 2. So zero won't be responsible for monochromatic edges. And there is a promise that there are at most one column with all one, and all other column are having Hamming weight 1 or 0. So the columns having Hamming weight 1 or 0 are not responsible for monochromatic clicks or monochromatic edges. Only columns with all one entry can be responsible. Column with all one entry is responsible for omega t many monochromatic edges. That is, all the edges of a particular click will be monochromatic. So formally, the strategy of the player is such that to ensure this following thing. If the graph has no monochromatic edge, there is no all one column in matrix M, and if there are omega t many monochromatic edges, then there is an all one column in the matrix. So with this thing, we are done with description of the reduction, and in general our the sketch of our lower bound proof for conflict estimation in random model, Bhattacharya model. Now let us have a look at our result table. So we mentioned that our result is about conflict estimation in all three Bhattacharya model, where our result in random model Bhattacharya model is the main focus. But we have also studied Bhattacharya model and Bhattacharya degree variable model, this model where the upper and lower bound are tight. Note that the upper bound and lower bound in this paper for conflict estimation in random order Bhattacharya model are not matching. There is a gap. So a natural question is our upper bound of cardinality V by root T is tight for conflict estimation in random order Bhattacharya model up to polynomial factor obviously. So this is the problem we are posing. We don't know the answer. It may happen that there is a better algorithm than our stated bound, or maybe the lower bound can be pushed up. But our hunch is that our algorithm is really tight up to polynomial factor. We'll be happy to know if the result can be improved in either direction, that the upper bound can be improved or the lower bound can be pushed up towards the upper bound we have given in this paper. We'll be happy to know about that. So thank you for listening.